Good afternoon, everyone. Welcome to IME 765. Today is April the 20th. Let's continue the discussion on linear regression 1, the OLS, the ordinary linear regression solution. First of all, let me share my screen and also stop the video here. Okay, so let me see. In the last class, we finished the Cholesky decomposition and we started the QR factorization, okay? So some very basic reviews. First, we have the full QR decomposition, factorization, it doesn't matter. And for the full QR factorization, it is for a given matrix A as in RMN, the A equals to QR, where Q is a full matrix, as a square matrix, and R is an upper triangular matrix. Okay, so here the Q matrix is orthogonal because it's a square matrix and all columns are orthogonal. Okay, by the way, the definition is QTQ equals to QQT equals to I. IM means the identity matrix with M dimensions, okay? And then we showed that the range of the matrix is actually equals to the range of the first part of the Q. The first part is the Q composed of the first n columns. Okay, so here we have, give me 1 second. Here we have A as m by n. So m is the number of rows and n is the number of columns. And then because we assume m is greater than or equal to n, so let me get my annotate here. Annotate. So your matrix will be something like this way. Your matrix Q should be something like this way. This is Q. And your R gonna be n by n. So R is gonna be something like that way. This is a full QR decomposition. Can I write something here? Let me see. Let me use a black color. This is gonna be Q, and this is gonna be R. The full QR decomposition. Okay. And we've showed that since span of this, let me change the color. Span of A equals to the first k column for any k in 1 to n. So that this shows us that we can actually make a thin QR decomposition, which is gonna be the case that Q is in n by, Q is in m. Sorry guys, I made a mistake. I made a mistake here. The one that I drew was actually the thin QR. Give me 1 second, because usually we use thin QR instead of the full QR. Give me 1 second. In the full QR, your Q is a square matrix. So let me use yellow color again. Okay, let me add a text. Where's text here? In the full QR, you're gonna have Q is a square. It's a large square, and R is m by n. That's something like this way. And this is your Q. And this is your R, okay? So Q is orthogonal, and R is upper triangular, means it's gonna be in this way. And all others gonna be 0. Okay, then because of this, so we actually know that we do, let me use another color, for example, this. We do have a thin version of the QR, which is, let me add the text first, which is a thin QR. It's gonna be in this way, that my Q is m by n, and my R, sorry, my Q is m by n, and my R is n by n. It's like this. And then let me use the color. So this is gonna be a thin version, Q1, and this is gonna be R1, okay? And R1 indeed, this time it is upper triangular. This is very simple. Of course, if your A here, it is a full rank matrix, then what's gonna happen is that your decomposition gonna be unique, and your R gonna be has full rank. Okay, so so this is the full and a thin version of the QR factorization, and the proof is rather simple. For the QR factorization full version here, you can prove it simply by what? By, let's say, the Gram-Schmidt itself is already a QR decomposition proof. And also, strictly, you can prove it by use induction. It's very simple. And after getting the full version of, after proving the full version of QR decomposition, the thin QR decomposition is rather simple, because by the structure of R, you directly get it, and also by, you know, the case here, the span of this. And okay, so we also mentioned the QR factorization and Gram-Schmidt process. Okay, let's briefly review it again using this example again. So the very first thing I'm gonna do is I'm gonna take A1. A1 is the matrix of A. A's are the columns of this matrix. And then I'm gonna let me make it bigger. Okay. And then I'm gonna, then I'm gonna set Q1 equals to A1 over its norm, so that Q1 is what? As a unit vector. Okay. Then for Q2 and Q3, what do I need is that first, both of them are unit vectors, meaning that the norm of them is 1. And the second, all of them should be mutually exclusive, should be mutually orthogonal. In other words, they are perpendicular to each other for any two pairs, right? Okay. So to make to this end, I make Q2 equals to this. First, I make a projection of A2 onto my Q1. Because Q1 is a unit matrix, a unit vector, so A2 onto Q1 simply equals to this. Let me use a yellow color. Okay, simply equal to this. Why? Because this part, it's not that clear. Let me choose another color. Sorry. Let me see which color is going to be better. Let's choose this pink color. Sorry for using pink color, but I hope it's going to be better and different from. Okay, good. From the existing colors. So this one is what? Is simply the coordinate, right? And Q1 itself is a unit vector, so that this directly shows you the coordinate of Q1 onto, A2 onto Q1. And this is orthogonal projection. And of course, this one must be what? Must be orthogonal to this one. Get the point? This is something similar as a triangle. Suppose you only have, okay, let me do it step by step. Suppose you only have this line first, and then here I have a direction. And suppose you have some light here. You have some light. Consider that there are some, a sun. For example, now it's not raining anymore. A lot of sunshine outside of the of your windows. You can see it, and the sun is completely vertical. Okay, so suppose this is a stick. You want to check what how large the shadow of the sun gonna be. Let me use another color. Let's say use a green color. So we should have something like this way, right? Something like this. So that this one must be what? Must be orthogonal to this one. You know what I mean? Because why? Because this is the sun. There's a sun, sunlight this way. So that this one must be 90 degrees. That's the reason why if we use A2 minus this vector, this direction, what? Must be perpendicular to Q1, okay? However, we cannot just simply use this one. The reason is because if we use this one, we cannot guarantee that it's a unit vector. And hence we use this one divided by its norm, so that Q2 is also a unit vector, and meanwhile Q2 must be perpendicular to Q1. Okay, and do the same for Q3. That is, first I have this A3, and then what I'm gonna have is, first I use this A3 minus this part. This part is what? This part is the is what? As the shadow of Q3. Sorry, the shadow of A3 onto what? Onto Q2 direction. See it? And then this part is what? This part is the shadow of A3 onto Q1. Project. All here project means orthogonal projection. Okay. So that here I have 90 degrees. Here I have 90 degrees. And hence, this part, which means this vector is what? This vector. This, it's even better. Okay. This vector is the summation of these two. And using exactly the same idea, if I use A3 minus this, then I will have this. See it? This direction. So I must have this direction, which is this one, which is actually, you know, this red dash line, this direction. This one must be perpendicular to both Q1 and Q2. See it? And again, to make it to be a unit vector, I use this one divided by its norm itself. So its norm, so that Q3 must be perpendicular to Q2 and Q1. And meanwhile, Q3, Q1, Q2, Q1, all of them must be unit. Clear? That's the way how I do it. I feel a geometric interpretation is better than algebraic interpretation. By the way, I gave you you guys an homework or an exercise last time. I don't know, did you do it? Which is substitute this to verify that this is really true. First of all, this 36b for sure is true, and you know, because I constructed in this way. So 36b is very simple. But how about 36a? This is the idea of a Gram-Schmidt process, okay? Gram-Schmidt orthogonalization. And again, I hope you guys can write the algorithm by yourselves. Do not have a look at mine. And the worst situation is what? The worst situation is, okay, let me ignore all the mathematics here. Okay, I just read this. I just code it one by one, done. No, this is the worst case. As a PhD student, you must, okay, understand the principle here, because this is a very simple undergrad level. Now, this is far from something, let's say later we're going to introduce Lasso, KKT, and SVD, something inside, you know, a bit more difficult. This is very, very simple. Almost everybody learned, not everybody, many people, I would say, learned in undergrad level. So you must understand the principle very, very clear, okay? And also here in the Gram-Schmidt method, we actually chose this RIK to be AK in the product of QI. See, the same. For example, suppose your I equals to 1 and your K equal to whatever. And then what you are doing is exactly this. See it? And you can do step by step. That first get Q1, and then get Q2, and then get Q3. You see it? And this is geometric interpretation. What you need to do is really plug in this, where your Q's equals to what? Your Q's equals to this, and plug in your RIK inside, and then to check whether this is really satisfied. Okay, you know what I mean? I don't know whether you did it. What I mean is you need to check this. You need to check this. First of all, you have QK equals to this, right? And then you also have what? You also have RKK equals to this, and also RIK equals to this. See it? So what you need to do is to plug in 37 and 36 and 38 into 35C. And then you have the QK. Then verify 36A is indeed true, algebraically rather than geometrically. And after doing that, you're going to see that, yes, indeed, they're correct. And as I mentioned the last time, you'd better check it until K equals to 4. That's going to be easier. You know what I mean? It doesn't matter what is A. but it doesn't matter what is Q. Okay, do it by yourself, step by step, very clear. Then you're gonna understand this Gram-Schmidt method more clear, and it's gonna be your method rather than you learn it every time you're gonna forget it. Okay, and today we're gonna mention another. By the way, the algorithms are here. And again, strongly recommend you write it by yourself instead of just looking at this. Very, very simple algorithm. And today we're gonna mention a modified version of Gram-Schmidt process. To make it more clear, I call the Gram-Schmidt method here to be classical Gram-Schmidt method. So this looks very good, and theoretically, clearly it's correct. But why we still need to modify it? Because as I remember I mentioned the last time, both Gram and Schmidt, there were people living in 19th century. So so at that time there was no computer, and of course at that time they just calculated numerical examples, a very small number, and mathematically of course it's correct. However, when we really apply the Gram-Schmidt method, the classical Gram-Schmidt method, process method, in the computer using high dimensions, and especially if some numbers are very big or very small, then the Gram-Schmidt method could have problem. Its conditional number is a big problem. Using a simple language, we can say that numerically the solution calculated by Gram-Schmidt method is not stable. An interesting thing is, after a very, very simple modification, this issue is going to be greatly improved. And until today, many apps or software calculating the QR, I believe MATLAB is one of them, calculating QR as using the modified Gram-Schmidt method. And that's really nice. And I think, Mahbuba, you may have already learned the Householder triangle method, right? In
Yes.
that book. Yes, and also there are some givens method. All of them are correct, of course, and all of them are very useful. The reason that I didn't show the household triangular here is because I feel Gram-Schmidt method is easier to understand. Household triangular, you need some very smart, very clear observations. And in Given's book, the reason, so sorry, not Given's, in this book, anyway, difficult to directly, let me see, where am I? I'm here. In this book, okay, in this book, it introduced household triangular first, and the Gram-Schmidt method is something like additional. The reason is because Dr. Golub, the first author of this book, is the one who invented householder. So of course, in 1965, he's the inventor of householder. So of course, for him, this is easier. So he introduced the householder in the beginning. For all other books that I've known so far, all of other books use the Gram-Schmidt method, Gram-Schmidt process first, then introduce householder and the givens. Okay, then let's have a look how we modify this Gram-Schmidt process. It's really actually simple. First, let's have a look at the Gram-Schmidt method. What we do is we can directly have a look at the algorithm here, make the life easier. What we do here is that in each iteration, we calculate the z equal to ak minus this, ak minus sigma of rk times qi, right? And this ak is fixed. And these qi's are something that we calculate gradually. For example, have a look here. See what we do? By the way, here the zk is actually this. These kind of things are the zk, okay? Z2 and the Z3, the numerator, and RKK is the denominator, so that you have Q equal to ZK over RKK, which is the norm of ZK, okay? So we, in conclusion, in the classical Gram-Schmidt process, what we did was to fix the AK, and then we gradually update QK. We gradually update RIK and QI, and then we have the next QK, right? Okay. The modification here is that I'm gonna fix my QK, but I'm gonna change the AK, the AJ here. So you may have a question, hey, AJs are the given number because A, matrix A equal to A1, A2, the columns, right? What I mean is this, right? This is matrix A. And you may question, hey, how can we change it? Okay, the truth is that we are gonna update, that's why I use the word update. We're gonna update this. And to avoid the confusion, I denote it as this, AJK. That means the AJ in the kth iteration, okay? In each iteration, I'm gonna update AJ, okay? And what we're gonna do is that we're gonna set QK equal to AK over, this AK means this one. I should write AKK here, divided by this. And let's have a look at the example. It's gonna be more clear. Again, exactly the same problem. Okay. So first of all, the same. I'm gonna first of all, let me make it bigger. First of all, I'm gonna make Q1 equals to this, the same. And for notation convenience, I use AJ0 to denote the original matrix. Okay. So you can have a look at here in the algorithm part here. See it? So my original A matrix equal to A10, A20, blah, 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 AN0. This is the real original A. Okay. Now let's have a look at here. So my Q1 is still the same, equal to A10 over its norm. Done. Okay. Remember in classical Gram-Schmidt method, how did we do? We calculate the projection, the shadow here, and use Q2 equals to this one minus this, right? And divide by its norm, and we get Q2. Remember it? Okay. Here, we do not do it. Instead, we do this. We actually update A21. This means the A2 in iteration 1. We update it to be what? To be A2 minus A2 inner product, A20, which is the original one, inner product of Q1 times Q1. In other words, this one is what? This one is the shadow. So what I did here is that I set A21 to be this one. And then I use Q2 equal to A21 over A21 norm. See it? So that this A21 is actually what? Is actually the same idea of what? Of this one, right? Of Z1 actually. Of this one. See the point here? Okay. So look, they are using exactly the same idea here. Okay. And now is the trick that not only for A21, I'm going to update for A31 as well. That in iteration 1, I'm going to update the original A30 to be A31, which is A30 minus A30 inner product of Q1. In other words, the second part is the shadow. Let me make it more clear. So this part is actually what? This part is actually this. See it? This is what? The shadow of A30 onto Q1. And this one minus its shadow. So A31 equals to this one, equals to this, this vector, okay? And now I go to, and now I set Q2 equals to A21 over its norm. So I have already had Q1 and Q2. Then I go to iteration number 2. So I'm gonna update what? I'm gonna update A32. I have A32 equals to, I think I have, give me 1 second. I'm afraid I have a typo here. This should be 2. This number here, A3 should be 2. Let me see. It should not be A31. Okay, no problem. It's here. This one. I'm talking about this one. Okay, so Let me see. A31. So to update this one, I'm gonna start from the last A3. The last A3 was A31. And then, so this vector equals to the projection of A31 onto Q2. And here we go. Again, here all the QIs are unit vectors, okay? So you directly have this one, right? And now I'm gonna take Q3 equals to A32 over its norm. And because this is 3D, so I've already done Q1, Q2, Q3, I'm done. Of course, if you have 4D, you're gonna continue it. So let's make a simple summarization here. Make it smaller. Let me open a Word document. Okay. Let's see the iterations. Okay. In the very beginning, what I'm set is this. I have Q1 equals to A1 0 divided by its norm. Come on. A1. To make my life easier, I'm not gonna write the parentheses here. Okay, I just directly write AJK like this one. Okay. Then the second thing is here. Here I'm gonna do what? I'm gonna update A2 and A3. So what I do is A2 1 equals to A2 0 minus Judas. I wish I have left and right angle, so make my life easier. Okay. Minus this one R12 times no, actually it is here. Let me copy and paste here. 0 and Q1. Okay. What I'm writing is right here. And we denote this part A20 Q1 to be A1 R12. Okay. And similar, we're going to update the A3. I can copy and paste. A31 equals to A30. Do all this to A30. Okay. Now I have already had this one, and then what I'm doing is here, step number 3 is to set the Q. So I simply have this. Can we just why so stupid? Okay. And then I have my Q2 equals to A2 1 divided by its norm. Okay, so I finished A2, Q2. And then the next step is what? The next step is to get Q3 and do exactly the same thing. Come on. Okay. However, this time you finished A2, you're going to only update A3. And you're going to have A3 2 equals to A3 1 minus A3 1 in a product of Q2. And then finally, you're going to have Q3 equals to A32. Come on. Divided by itself, the norm of itself. Okay, that's more clear. Oh, wait 1 minute. I can also make the font to be bigger. Nice. Okay, clear? That's how we do. We first get this one, and then we update A20 to be this one. Okay, and then Q2 equal to this. And then we also, meanwhile, in iteration number 1, we also calculate this. Make my A31 to be this. This one minus its shadow onto Q1. So I have this. This is my A31. And then in the second iteration, what we do is that we update A3 again. We use this one minus its shadow onto Q2, which is this. And I finally have this Q3. Actually, I have this one, which is A32, I should say. And then use A32 divided by its norm, I get a unit Q3. Okay, so that is the way we did for the modified Gram-Schmidt method. And you see what the basic idea of this and of this are exactly the same. Get a point? But what is the difference? The difference is that here I'm gonna accumulate all of them together. For example, I'm gonna calculate all of them together, done. And this is Q3 done, right? Suppose I have a Q, let's say 100. What you're gonna do? You're gonna have, A100 minus A100 times inner product of Q99 times Q99 minus A100, let's say Q98 inner product of this one Q98 times Q98 and blah, blah, a lot of things. Do all together, right? But the Gram-Schmidt method, you see, what is the difference? The difference that in each iteration, I'm gonna update the AJK one by one. See it? So the difference is that instead of calculating all of them together, I calculate step by step. And it can be shown that the numerical results are much more stable. Okay, any questions here about the Gram-Schmidt method? The QR factorization together with the Gram-Schmidt and the modified Gram-Schmidt method, you do need to spend the time after this class. It's impossible that you don't do any, let's say a review or something and you directly learn it in no way. Especially for Europe. I don't know whether you've seen this before because Mahabuba, he has already done some research 1 year ago regarding this. So I guess he should at least know, have heard of this kind of concepts, and I hope you still remember, the practice that one last year. But Europe, if you've never used QR factorization before, you need to check this very carefully. And the QR factorization and the SVD, singular value decomposition, they are extremely important. Many problems are actually some very, very classical famous methods are derived by them. Okay, so any questions about the Gram-Schmidt and the modified Gram-Schmidt method? No question? Okay, then let's continue. So what is the point for us to introduce the Cholesky decomposition and the QR factorization? The point is that if we have this, then we can solve the OLS solution much easier. Okay, have a look at this. What is the OLS solution? The OLS solution, assuming full rank, okay, actually full rank. The OLS solution is this, right? But okay, I cannot tolerate it anymore. Let me, okay, still good. Beta equals to this. And the big problem is this inverse, right? Okay. Now let's have a look. What's gonna happen if we first use Cholesky decomposition to solve it? So by the Cholesky decomposition, we actually, the normal equation here, we want to solve this. Okay, So what we are going to do is that we are going to do the Cholesky decomposition for this xtx. So for notation convenience, I set C equals to xtx. Xtx, again, because we assume full rank of x, so it must be positive definite. And then it should be p plus 1, I think. Anyway, it's a typo. Let me check. Go to someone. Let me see whether I can do it right now. Okay, yes, I can do it. Compile. Interesting thing is that doesn't work here, and I have to manually use my mouse. Why? Okay. Yes, it's p plus 1, the dimension. And by the theorem 1, which is Cholesky decomposition, since this is a full rank, so we must have a unique Cholesky decomposition. Let it be C equal to LLT, where L's are lower triangular. Okay, so now this one becomes what? This one becomes LLT beta equal to XTY, right? Okay, now L is lower triangular. So what? So we can solve this. We can let this part to be, for example, Z. What's so big? Make it smaller. So suppose this part is Z. So we solve this. It's very, very easy to solve Z because L is lower triangular, right? You get a point. Why lower triangular? It's very, very simple. Because you only need to solve the first one. Then have the first one is substituted, you get a second one. Substitute, you get a third one. You know what I mean? That's why lower triangular for solving this kind of problem, it's extremely fast, extremely easy. Okay, so once I solve the Z here, and then I solve this equation, LT beta equal to Z. And again, this is extremely fast. Why? Because LT is upper triangular. See it? So in this way, we don't have to brutally calculate the big inverse matrix of XTX. Instead, we run the Cholesky decomposition, and we solve two very, very simple equations. The first one is lower triangular, and the second one is upper triangular. Get a point? That's the reason why. And this is much, much faster than you brutally solve the inverse of XTX. It's going to be much faster. Okay, any questions here? I think this is very simple, very clear and simple. The key is actually you need to know how to do the Cholesky decomposition, which is right here, given by, did I write an algorithm here? I think I wrote, yeah, which is by here. Okay, the Cholesky decomposition. Two things I still want to mention about using the Cholesky decomposition. I think it's right here because what happened here? Come on. That's interesting. When I'm running the Zoom, this latex becomes very unstable, and I don't know why. And I cannot use a keyboard to compile it. Anyway, have you met this kind of situation, Mahbuba? No. Later, if we have meeting, run the text. Or if you use overleaf, that's another story. I'm using Text Studio, and I found something interesting. When I'm running the Zoom, it's not that stable. Anyway. Okay, so the next thing I'm going to introduce is to use QR factorization to solve the problem, to solve this LST problem. First of all, is this. I have x equals to QR equal to this, okay? And this is the full QR decomposition of x. And then what I'm going to do is that for notation convenience, I set QTY equal to this. AB. Note that all these are constants, okay? Suppose I've already know Q. All these are constants. Okay, so what I'm gonna have is what? Is A is P plus 1 dimensions, and B is N minus P minus 1 dimensions. Okay, now let's calculate XB minus Y, X beta minus Y. This is actually the RSS. What's gonna happen? So I time QT in both sides. And as we mentioned before, that since Q is a unitary matrix, right, or orthogonal matrix, any norm times an orthogonal matrix equals to itself. Remember, what I'm saying is this. Let's see. Norm of A equals to norm of QA. Where Q is a unitary matrix. Can someone tell me why? How to prove it? Ara? Still remember how to show this one? By definition, directly. Hello, Ara? Can you hear me? Hello, are you there, Arab? You need to unmute yourself, otherwise I cannot hear you.
Oh, yeah.
Okay. Remember how to show this one?
Q is unitary, so Q over Q mod of Q is 1, right?
Yeah, that's it by definition. Okay. This let's say Q norm. I mean square. Make it easier. Square. Okay. And this one equal to what? This one equal to ATQ. QA, right? Equals ATA, done. Equals norm of A square. Okay, very simple. So here the same. What I'm gonna do is x beta minus y as a vector, right? I time a qt. Q is unitary, of course, qt is unitary. So the norm should be the same. Now let's see what's gonna happen. Your x equals to what? Your x equals to qr, right? And qt times q equal to unitary, equals to I. So you have an r here. R equals to r10 times beta. And qty we've already denoted to be AB. Here, this R1, the dimension is what? R1, the dimension is P plus 1 by P plus 1. And your A is also P plus 1, okay? And so why I'm writing this way? Because be careful, this R1 and this Q, both of them are what? Are constant. I know it. You give me an X, I directly give you the R1 and the Q, right? Okay, now what we have is, this is what? This is a variable because I can change the beta. However, this part, the B here, is a constant. Why? Because B here simply equals to the last n minus P minus 1 dimensions of the vector of qty, where qty is a constant. See it? And that's the reason why this part, I mean, if you write it a bit more, then you can have this part equals to R1 beta minus A norm plus B norm. See it? By the way, do you have any questions? Why from here to here? This should be very clear, right? Any questions from here to here? Very clear, okay? So because why? Because simply this one is you just put them there. That's just very simple. You just put them there, you know, and then the block matrix, okay? And that's gonna be, this 0 is still 0, so that you have R beta minus A, and this part is 0 minus B. And the norm, of course, is that part norm plus this part norm by the definition of norm itself, right? And this B is a constant, so I only need to solve this one, right? Which is R1 beta minus A norm. Okay, now how to solve this one? Very important thing is what? Very important thing is X has a full matrix. Because X has a full matrix, so what? So that my rank of R1 must be full. Must be P plus 1. In other words, my R1 must be a full rank matrix as well. Be careful that here R1 is a square matrix. This means, of course, R1 is invertible. Okay? This means you must have a solution of this, which is simply beta equals to R1 inverse of A. See it? And hence, you can directly solve the beta. And you may say, okay, so you still need to solve inverse. So what's the difference between brutally solving this one? The difference is that your R1 is what? An upper triangular matrix. So this 42 is extremely simple to be solved. Get a point? R1 is the upper triangular matrix. Any questions? And that's how we can solve it directly by the QR factorization. What you need to do is just to get the QR factorization so that you get the Q and R and you get A and done. Any questions? No question? Okay, in the following, let me introduce you another method, also QR factorization, but and basically they're the same, just play some interesting games, which may be easier. I don't know, more difficult or easier. For me, the same, no difference. It's in this way. So we have, well, let's start from the very beginning. Beta equals to, let me see. Okay, anyway, tired to make it. -1 and xt, xt, y, right? And this equals to what? Okay, anyway, I'm lazy to do this. Just to let you know, all of these are vectors or matrix, okay? So all of them theoretically should be both. I wish I have BM here. And let's plug in. My x equals to what? Equals to QR, right? Okay, so that here I have RT, QT, QR inverse, inverse, and then xt is again RT, QT, y. And then it equals to what? It equals to R inverse. R inverse must exist, okay? The reason I just mentioned. This is the thin version. Okay, let me write it down like this way. Consider the thin QR factorization for x. X equal to QR. This is the thin QR factorization, okay? So that my R is a squared matrix. And as we just mentioned here, R must be a full matrix. Let's say where X has full, let's say, column rank. Then we have this. And this equal to R inverse and then RT inverse. Make my life easier, I directly write R negative T. This means RT inverse, okay? RT inverse and R inverse T are the same. And then RT QTY. And see, what is this? This and this cancel, see it? So that you directly have this part. So you have your beta hat, which is OLS solution, ordinary linear square, least square solution equal to this. Get it? And then let's have a look what's gonna happen for what? For the y hat. Y hat equals to x beta hat. And this equals to x equals to QR, beta hat equals to this, R inverse QT. And see the point, it's already here. So this equals to, be very careful, this equals to QQTY. And you may ask, hey, why not QQT equal to I? Because this is the thin QR factorization. Okay, this Q is not the orthogonal matrix, not the orthogonal matrix. It's not a squared. So that you only have QTQ equals to Y. Get the point? Check it here very clearly. Where's here? Let me see. Where's the thing here of factorization? Oh, no. Again, it has something here. QR factorization, and here is thinker of factorization. Check here. Q1 has orthogonal columns. See it? So if Q1 has orthogonal columns and the Q dimensions are by m by n, okay? It's not m by m, it's no longer square. So you cannot write Q1 inverse. There's no Q1 inverse, okay? And I think I added something here, and I don't know why it comes here. So here you have Q1T, Q1 equal to IN, but you do not have Q1, Q1T. Why? Because think about this. Q1T, Q1 means what? Means the column. Suppose your Q1 equal to this. Different columns, right? So this is Q1, for example. So what is Q1T by Q1? Q1T by Q1 means this. They become rows. And the rows times the columns. See the point? That's the reason why they must be I. You know what I mean? Because this and this, this and this, they are orthonormal columns, so that inner product of itself must be 1, and inner product of any of them, two of them must be 0. That's the reason why QTQ must be identity matrix, but QQT is not necessary to be identity matrix. And then let's continue. Here I have QT, QY, and indeed I need R inverse QTY, QT, and I get this. And for calculating the Y, I even don't need this R. Get a point here? And everything after the calculation is going to be much easier. Okay, so this is how the QR factorization can help us to greatly reduce the calculation work of brutally calculating XT X inverse. Any questions here? No question? Okay. And then it's a very short discussion about what if the matrix itself is not full rank. So first of all, it's not good. Why? Because you're going to have a lot of solutions. Why? Think about this. Suppose beta is a minimizer, and let B be the null space of this. Then beta plus B must also be a minimizer. This is very simple, right? Why? Because what does the null space of X mean? That means X times B equal to 0. See it? So, and then consider beta plus B. You have X beta plus XB. XB is 0. So of course, any of beta plus B must be a minimizer. You may want to argue that you said, hey, so what if I do this? So let's say in the full rank case. So why you said it's unique? Because for the full rank case, the null space of X is only 0. Right? That's the definition. Because my matrix is full rank. So if my X times, let's say a B equal to 0, there's only one case that a B equals to 0. That's it. So that beta plus 0 equals to beta self. That shows that beta is unique. But here it's not unique. Then there's a problem. So which solution you want to get, since it's not unique, right? So usually what we excuse me. Usually what we want to get is the solution with the minimum 2 norm, which is called the minimum norm solution. And we can use some standard methods, for example, numerically, okay? We can use some standard method like singular value decomposition, or still use QR factorization, but need column pivoting technique. Then we can still handle this situation. And I'm not gonna introduce this part too much because it's gonna take a lot of time, about details. If you like, just have a look at the book here, the book that I just showed, the numerical, what's the name? Matrix Computations. That's in chapter 5.3, okay? And another thing is really worth our attention is that what if P plus 1 is greater than N? In other words, the column is greater than the row of the matrix X. And you may say, hey, it's very abnormal. Yes, it's abnormal. Unfortunately, this situation happened a lot in some areas, especially in pharmacy, let's say in drug testing. The main reason is because to finish one test, it's going to be very, very costly. Okay, so I don't have too much time and too much money. Costly means both time and money. So I don't have too much time and money to do a lot of tests. Instead, I have only limited tests, but I do need to consider a lot of chemicals, this kind of parameters. You know, if you have read some paper in this kind of medicine, or let's say drug tests, you're gonna see they consider a lot of parameters. Then it's gonna be a disaster because it could be the case that p plus 1 is greater than n. For example, p equals to 1,000, n equals to 10. It's possible. In this case, all the system that we've built so far will have serious problem. How to handle this? It's going to be some shrinkage techniques, or let's say sparse regression, which will be introduced in the next 2 lectures. Okay, so the details we're gonna put it after it. However, in most this kind of commercial software or apps, it's gonna first check whether they're kind of like a redundant columns. If there are some redundant columns, then they're gonna try to eliminate this kind of redundant columns. The cost is very simple, just a Gaussian elimination, which is very fast. So it's almost for every app, it's gonna be the first step to do it. Okay, so in the following, we always assume that the input matrix is a full rank. Okay, and the next one I want to introduce is something about regression with multiple outputs. So far, what we have seen is a model like this way. So I have only one output for each example. For each sample, I have only a y1, a yn. For the multiple cases, what if I have a y11, y12, y1k, or y1m, let's say, k equal to 1 to m. I have multiple output. What shall I do? Okay, so in general, the model is in this way. The model is in this way. For k equal to 1 to m, I will have correspondingly, I will have a beta 0, 1, 0k as well. 0k, 1k, blah, 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 until beta pk. Okay, so the beta I write in this way to be a matrix which is in p plus, here's the typo again. It's gonna be p plus 1 by n. Okay, so this is my betas, and my y's gonna be in this way. Okay, all these are vectors. Okay, y1 vector, y2 vector, yn vector. This is gonna be Rn by n. That I assume I have n observations. The outputs in one sample. I have n outputs, and I totally have n samples. Okay, and this epsilon is the noise. And later we're gonna assume where this. Later, we're going to assume, for example, suppose this epsilon follows normal distribution, then something's going to happen, okay? And so the notation is in this. My E is the epsilons, okay? And let me see. Why these epsilons are so small? Because here are these epsilons are vectors, okay? They're not, this kind of very small epsilon. I didn't use the bold, the BM, but it showed looks like a scalar. However, if you compare this epsilon versus this epsilon, you can see this is indeed bigger already. Okay, now let's calculate the RSS, the residual sum of squares of the B matrix here. Again, here B is a matrix because I do have multiple outputs. Okay, so this is defined in this way. What I'm gonna do is that consider this case only. Suppose there's no k. This part is what? Is nothing but a single level regression RSS. See it? Now, since I have totally n outputs, so I'm gonna sum from k equal to 1 to n, and this equal to this. And by some notations, you can write it in this way. This is also inner product, but the difference is the matrix inner product, not a vector, inner product. The same. Arab, I think you have learned this in my 770 class. Remember it in CLP, conic. Remember linear program? We have used a lot about this kind of the cone, a lot about this kind of inner product. Okay, so for a matrix A times B, inner product of B, it's a scalar. It's not a vector or matrix. It's a scalar. Nothing but the dot product of all elements. Of course, you have to guarantee that A, B are the same dimension. Okay, otherwise you cannot do the inner product. The same as inner product of vectors. The difference is that here I have more dimensions rather than just one vector. I have, let's say, m vectors. Okay, so in general, if I have A dot B, the inner product, I can write it in this way, equals to the trace of AT times B. The trace, remember the trace, the sum of diagonal matrix, the diagonal elements. Okay, this is very, very easy to be verified. You just think about it, you're gonna get this solution. And hence, I have this. From this to this, I have this. Okay, now the question is how to minimize this RSS with respect to B. To this end, I checked several books. Most of the book, I don't know why they use some statistical properties and make the proof or the steps very complicated. I personally don't like it. So I personally use an OR way to directly prove it, and it's extremely simple. and first of all, the definition of this one is this, right? And where I have the k equal to 1 to m. So this one is another version of this, because again, suppose there's no k. This part itself simply shows, if there's no k, this part shows you what? The RSS of one output. And since I have k output and n outputs, so I just sum all of them and I get this part. Okay, and then clearly this is going to be greater than or equal to this. Put this sigma out. Why this is correct? Consider this. Actually, this is, for this part, I'm talking about this. The minimum of x, let's say fx plus gx. This one must be greater than or equal to this, fx plus mean gx. Why? Why? It doesn't matter x is, let's say, okay, you can even give it a region. Who cares? X is whatever region. It doesn't matter whether it is convex or not, or how does F look like or something. It doesn't matter. Any idea why this must be correct? Quick. This is very, very simple, extremely simple. First of all, think about this. Suppose the solution of this part is xf star, and this part is xg star. The thing is what? The thing is, in most cases, xf star and xg star are not the same, right? So that if you take something can satisfy this but cannot satisfy this, and vice versa. And that's the reason why this one would not be as good as these two. However, you may say that, hey, this is not really strict. So the strict way is the same. It's just really simple. You plug in, for example, xf star. Then you're going to show that this one is greater than or equal to, sorry, let me see this. This one is less than or equal to this plus, plugging this one inside. And then let me think about that. How to show that if I use this way, it's not that strict. Okay. Easy. Get the solution. Suppose the x star is the solution of this part. And then plug in, you're gonna see that if you plug in this fx, so okay. Let me write it down. Let x star be the solution to the left-hand side, okay? Then you must have fx star as greater than or equal to f star. And g, suppose x star is feasible. Suppose that's feasible, okay? And the gx star as greater than or equal to g x g star, and done. And that's the reason why the sum of them must be equal to greater than equal to the sum of this. Okay, so this is a very brief proof. And now let's have a look at this. Isn't it the same? However, here I have m functions rather than 2 functions. So suppose each of this function is what? Each of them is an f, let's say, kx. Now what you have is the minimum of summation of fkx as greater than or equal to the summation of minimum of fkx. See it? Exactly the same here. Exactly the exactly the same here. The same here. See it? You have f1, f2, f3, fk, fn, and here the same. So this one is greater than equal to the mean. This one is this one is greater than or equal to this, the summation of the mean. See it? Okay. And now let's have a look. However, the interesting thing is that this solution is feasible. That you let bk equal to bk hat. It's feasible. And now you have what? You know that a solution plugging, this this part for the b hat equal to beta 1 hat, beta 2 hat, beta m hat. For this part, what is here? For this part, it must be what? It must be less than or equal to any other feasible solutions. And this solution itself is also feasible. This tells you what? This tells you this solution is the minimum solution, the minimizer. Get a point? The logic is this. Consider you're minimizing a function like this way. Let's say you're going to minimize fx. What you know is that fy as, okay, let's say x is in x. What you know is that fy will be less than or equal to any x for all x in x. And you also know that y is in x. Okay, this tells you what? This tells you y is the minimizer of f. Get a point? So here you go. This is the logic. So this tells me that this b of this solution is feasible and it's less than or equal to any feasible solution here. So this one must be the minimizer. And I want to change this beta. Let's see, where is the problem here? Okay. Let me take the underline outside. Then run it. Now it's going to be more beautiful here. Okay, good. And so that I have this solution. However, there's a problem. You may say that, hey, in real applications, for example, I have different observations. For example, let's say the first column of y, for example, okay, indicate, for example, the salary. The second column of y indicates, let's say, some bonus. The third column of y indicates, let's say, what else regarding money? Let's say some extra money, for example, if you invest stocks. So clearly, salary is the most important thing. So why should I calculate in this way? Because I may have a different weight, right? The salary, the y1 part should be the most important part. y2 the second, y3 is the least important. So in this case, I may have a weight for these columns. In addition, for the rows, I may also have a weight. Why? Because this, for example, let's call it, let's say, Yij, The J may mean time, the time t. You can use YIT. So the closer the time it is to me, the higher weight it should be, right? So in general, I want to consider this problem, the weighted least square problem. And this problem can be written as this one. And this, the solution can be in this way, written this way. And remember here, we also discussed this in where it is. Here we go. We also discussed the weighted least square problem. This is actually used in IRLT, in the logistic regression, remember it? So the thing is, we calculated this one by what? By the derivative, right? So do we have to use the derivative for the matrix operations again? And then later, maybe we will need to use tensor notations to denote it. The truth is no, you don't need it here. The truth is that you don't need it. You know why? Let me show you another method how to directly write down this solution, which is going to be easier than make the derivative. Think about this. Suppose I have y equal, okay, let me use a y1. Let's make it a one dimension, make my life easier. Equal to beta 0 plus beta 1x11 plus beta, how many betas did I say? P, right? X, let's say 1p. Suppose I have this. Now I want to add a weight to that. W1. Then what's gonna be? What's gonna be is that you're gonna have this. W1, y1 equal to W1 times this, isn't it? In other words, you multiply both y and the right-hand side of the first row of x by what? By W1. See it? Okay, now have a look at W. Let me see. I'd better use square root. I'd better use square root of W1 instead of W1 to make my notations consistent. Square root of W1 and then square root of W1. So that in the matrix expression, what I have? I actually have W half x equal to W half x, and my y vector equals to W half y. Okay, now you plug in this one into the ordinary least square solution. See this? X equal to W half x, y equal to W half y. Plug in, what do you get? xt gets out W half, and then W half times W half equal to W. Be careful that by our notation setting here, W is symmetric. Okay, so W half t equals to W half, and the W half times W half equals to W. So here I'm gonna have xt Wx inverse, and here is what? Here is again xt W half, and then y is W half y. So that here it's gonna be xt Wy. Isn't it exactly the same? Get the point? So this is a very easy way to interpret it. Okay, now let's go back to the multiple output to see how to use this way to explain our solution here. In other words, I'm not going to use any tensor, notation. I can directly simply use this idea to understand and prove that this is indeed the solution. In this case, you're going to have what? You're going to have exactly the same. First of all, from 48, I know this is the least square estimator for the multiple output linear regression, right? And then set xt equal, set x the same here, equals to W half x, y equal to W half y. And you're gonna have exactly the same thing. And you may want to argue that, hey, it's kind of like unfair. Why? Because the W there in single level or single output, my W's are simply what? The WI here, square root, of course. But how about my W here? Are these still kind of like WIs? And the truth is yes. The difference that here is going to be a WK instead of a big W. You know what I mean? Because if you have a big W, you will have problem. Why? Because in this case, you do need to have a tensor expression, which tensor is a higher level of the matrix. You know, matrix is 2D, so that in the one level of tensor, it is a matrix. Okay, so to avoid this tensor expression, I write it in this way, that the beta k WLS means weighted least square equal to here xt wk, where wk is defined in this way. Okay, so in this way, then yes, I have all the wk's, and of course you combine all the wk's together, you have a w, and here we go. Okay, and something similar is a similar question is, all here we assumed that the epsilon k's are independent. But what if epsilon k's are dependent? For example, what if we have a covariance matrix? In this case, what should we do? First of all, we define the y to be this way, where all this, this notation means there are columns, and this notation means there are rows. Each eta it means the ith row of matrix Y. Okay, and what we're going to do is that we're going to define in this way. Oops. We're going to define in this way. So this shows you the covariance matrix, and this is what? This is nothing but the just itself minus the estimated number, the truth, the observation minus this is a row. Okay, be careful. Eta 1t is a row. So eta means the transpose of the first, eta 1 means the transpose of the first row of y minus fxi. Fxi means the ith output, estimated output. This times this times this. Remember where you see this one before? Normal distribution. Multiple normal distribution. So it's very common that we assign, we use this definition. And similar, we can do some calculations. However, unfortunately, for this problem, there's no so beautiful explicit solution. And people solve it using numerical methods. And this part is actually very, very deep. It involves a lot of this kind of further explanation and statistical, properties. And here I'm not going to introduce it in detail. Okay, so this is a very rough explanation about linear regressions with multiple outputs. And in the next class, I don't know why it's in this way here. In the next class, we're gonna introduce one special case, which is the linear regression of categorical outputs. And I think this is everything about today's class. Thank you very much. By the way, please do these two by your hand, by yourself. Step by step, verify this. And the very important thing is verify this one is correct. Okay, it's gonna greatly help you understand the Gram-Schmidt and also the modified Gram-Schmidt processes. And that's everything. Thank you very much. Have a good evening. Bye.
Bye.